All right, let's get right into it. Today, we're going to unlock one of the most fundamental rules in all of physics, Newton's second law. It's this incredibly powerful yet simple cause and effect relationship that explains, well, why pretty much everything moves the way it does. I mean, look at these. A stalled car, a basketball, a rocket sled. What on earth could they possibly have in common? Well, they might seem totally unrelated, but believe it or not, a single really elegant law of physics explains how every single one of them moves. And by the time we're done here, you're going to see that invisible connection that ties them all together. Okay, so to really get a grip on this law, we've got to start with a super basic question. What actually makes something move? Or more accurately, what causes something to change its motion? Well, in the world of physics, any change in how something is moving, whether it's speeding up, slowing down, or even just changing direction, has a name. We call it acceleration. And here's the kicker. It turns out that acceleration is only ever caused by one thing, a net external force. All right, let's really dig into that idea, a net external force. Because that word net is super important here. It's not just any old force that does the trick. It's the total, kind of leftover, unbalanced force that's the real star of the show. So, picture this. You've got a couple of students trying to push a car that's stalled out. Their push, that's what we call the applied force. But they're not pushing in a vacuum, right? The road, the tires, there's friction, and it's pushing right back at them, fighting them every step of the way. This is where net force comes in. It's the only force that actually makes the car accelerate. You can think of it like this. It's what's left over after that tug of war between the students pushing forward and friction pushing back. It's that final winning push that actually gets the car to start rolling. And this brings us to our first big takeaway. The amount of acceleration you get is directly tied to the size of that net force. The students, they're only creating a pretty small net force, so the car barely speeds up, a small acceleration. But bring in a tow truck, whoa, that thing creates a massive net force, and you get a massive acceleration. It's a really simple relationship. More net force equals more acceleration. Simple as that. But wait a second, force is only half of the equation here. To really understand what's going on, we have to look at the other side of the coin, the object itself, and its own kind of stubbornness to being moved at all. Think about it. If you give a basketball a good push, that's our net force, what happens? It takes off. It accelerates super quickly, super easily. It really doesn't put up much of a fight at all. Okay, but now, what if you take that exact same push and apply it to, say, a huge SUV? What happens then? You guessed it, pretty much nothing. You get this tiny, almost imperceptible little nudge of acceleration because that SUV is just so stubbornly resisting any change to its motion. And that property, that resistance to being accelerated, that's what we call mass, or you might hear it called inertia. Basically, the more mass something has, the harder you have to push to get it to accelerate. That SUV has a lot more of that stubbornness than the basketball does. So let's recap. We've got two big ideas on the table. 1, net force is what causes acceleration. 2, mass is what resists acceleration. Now, what happens when we put those two puzzle pieces together? Well, we get the whole picture and, yeah, one of the most famous equations in the history of science. It just makes sense, right? We've seen that your acceleration goes up with more net force, but it goes down with more mass. It's a trade-off. And these two ideas combine perfectly into one simple, almost beautiful relationship. And here it is, the law itself. F net equals ma. The net force acting on something is just its mass times its acceleration. That's it. That's Newton's second law. So simple, but so powerful. This little equation is the key that unlocks the secrets of motion. And this is not just some neat little theory to write down in a notebook. No way. This is an incredibly powerful tool. It lets us predict and calculate exactly what's going to happen in the real world, even when things get, well, pretty extreme. So let's put it to the test with something awesome, a rocket sled. Okay, here's the problem setup. We know the mass of this whole system is 2,100 kilograms. We want it to achieve a frankly insane acceleration of 49 meters per second squared. And we also know that friction is trying to slow us down with about 650 newtons of force. So the big question is, how much thrust does each of those 4 rockets need to pump out to make this happen? This is where F equals ma becomes our best friend. we can set up the equation perfectly. So, on the F-net side, what's our total force? It's the push from the 4 rockets, let's call that 4T, minus that pesky 650 newtons of friction. Okay, and on the MA side, we just plug in our numbers, 2,100 kilograms times that 49 meters per second squared acceleration. Now, all we have to do is solve for T, the thrust for just one of those rockets. And when you run the numbers, the law gives us the answer. Each single rocket has to produce a whopping 25,000 newtons of thrust. That's just incredible. And that's the real power here. It's not a guess. It's a precise, predictive number. And these rocket sled tests, they weren't just for kicks. They were actually used to see what the human body could take, pushing physiology to the absolute brink. I'm talking about test subjects experiencing 45 Gs. That's 45 times the normal force of gravity. It just goes to show you how this fundamental law holds up, even in the most insane situations you can think of. So from now on, whenever you see anything speed up, slow down, or change direction, whether you're tossing a ball, watching a car accelerate, or even just feeling yourself get pushed back in your seat as a plane takes off, you'll know the secret. You'll know the rule that's making it all happen. F equals ma. It really is everywhere.